Say it again. 11:30 for you. How about that? Now, that assumes that I will have the exam ready by 11:30 because there's no exam yet. OK, the light is on. So we need to complete these lectures on second-order ODEs. And so let me do the following thing. We went very fast through this variation of parameter method. So I just want to spend 3-4 minutes to repeat what the method was. So we are trying to solve the equation that you see there on the top. OK? And we assume the coefficients to be functions of time. So it's a general ODE, but it's a linear ODE. All right? Still linear ODE. So the idea of the method is to compute first the solutions y1 and y2, the fundamental solutions to the homogeneous problem. And rather than taking a simple linear combination of those that will give us basically the solution to the null problem, take a combination that involves these functions u1 and u2. So the whole idea of this method is to compute what these functions are going to be. Okay? And the method, and you already have used it in your homework, it actually works nicely, but it leads to some integrals. And those integrals may not be easy to compute. So it's not like nothing is for free. So it works, but somehow you have the complexity of computing these integrals. So how does the method, how do you compute u1 and u2? The algebra is literally given in an example before this slide that you should read. But I'm going to summarize what the methodology is. It's very simple. We need two equations to compute these two functions, u1 and u2. So the first equation that we introduce as a constraint. So here the idea is, don't ask me from where is this coming. It's coming to simplify the method. That's what makes this method what it is, OK? So we are going to assume that u1 prime y1 and u2 prime y2 equal to 0. OK? No questions asked. We take it for granted. It's not like from where is it coming. It's coming by the genius idea of someone said, if I do this, the whole method is simplified. OK? And then there is a second equation that looks like u1 prime y1 prime plus u2 prime y2 prime equal to g. G, remember, is the forcing term. This equation comes by plugging in the approximation for y that we have there inside the differential equation, using the first constraint that we have here, and also using the fact that y1 and y2 are solutions of the homogeneous equation. So basically, when you plug in, after about 2 lines of calculations, nothing major, you will get terms like u1 times parentheses y1 double prime plus p y1 prime plus q y1, and that is 0. And similarly, you will get something like that for y2 that is 0, and the only thing that is left is u1 prime y1 prime plus q2 prime y2 prime equal to g. So you have two equations for the two functions u1 and u2, and you know how to solve a system of two equations with two unknowns. So when you do that, obviously you can see the coefficient matrix there is the Roskian y1, y1 prime, y2, y2 prime. It's here. And you can write the solution directly as what you see on these equations. And obviously, these equations give you derivatives for u1 and u2. So you're going to have to integrate. And literally here, we're looking for a particular solution. So when you integrate this and you have constants of integration, don't bother about the constants of integration, right? So you can take those to be equal to 0. So basically, what we're interested in is this integral here for u1 and this integral here for u2. OK? So this method always works, assuming you can compute the integrals. And even if you cannot compute the integrals exactly, certainly we can calculate these integrals by numerical integration with quadrature. So that should not be a problem. So I have an example that we try to finish on the last lecture, the last seconds, basically, of the lecture. So the example was very general. We said, let's take that the homogeneous solution was e to the s1t and e to the s2t. So for example, we can take here s1 and s2 to be real. So these are the roots of the characteristic polynomial. So we are looking for a particular solution of this form, u1 e s1t and u2 e to the s2t. And you calculate w. It comes to be this nice formula, right? So this is y1, this is y1 prime, y2, y2 prime. Nice. And then you plug in things inside the integrals. And you notice, OK, I see a type already there. I was going to say I have changed the variable of integration to tau to not confuse it with the time t where we do the computation. OK, so that t there should be a tau. I should correct it as soon as I go back. So if you plug in things, right, for S1, I mean for Y1 and W, you get this final wonderful result. And as you know by doing the homework problem, everything that you see inside that integral in parentheses, so that parenthesis divided by S2 minus S1 has to be the impulse response. Because if you know the impulse response, G, you can write the response to any forcing function f as such, right? Using this idea of convolution. So you can think, if you're putting a function as the driving force for the equation, it's like having a different delta function at each time, right? So if you know the response to the delta function, which is the impulse response, you just have to multiply with the instantaneous value of that function. So this formula is extremely powerful, and it is very general. If you know the impulse response, then you know the response to any function f of t. Remember this for the exam, just in case something comes to my mind that relates to this problem, OK? By the way, when you submit your homework, if your impulse response doesn't look like what you see here, then go back and correct it. And when I say correct it, don't just say et cetera, and here's the answer. Derive this answer. OK. All right, so let's move to, we don't want these things. All right, so we need to finish this lecture on mechanical vibrations. There is absolutely nothing new on what I'm going to do now, but we will basically limit our thinking to problems related with vibrations. And vibrations is a very general topic, right? It doesn't have to be mechanical vibrations. It can be electrical vibrations, can be oscillations in fluids, can be many different things. But right now, we're going to think of a spring with a mass oscillating around an equilibrium position. So some notation. We are going, so M is the mass. Capital L is going to be the equilibrium position of the spring. You know, so if you put the mass and you let it find its equilibrium location, that would be capital L. The total displacement past the equilibrium location would be, and again, I see another typo there, should be L plus U, capital L plus U. So little u should be the displacement from the equilibrium position, OK? And we're going to assume that there is a spring constant. There's a spring force that is linear in the displacement. And also, we're going to use some damping to make the equations of interest. So let me just go directly to some of the key equations. So I mentioned that capital L is the equilibrium position. So at equilibrium, the force by the spring is K times capital L. So that needs to be balanced by the weight. So mg equal K times capital L. We're really interested in displacement past that equilibrium point. And And we're going to assume for the spring force to be linear. And by the way, just to make things clear, because later on we will discuss nonlinear vibrations, where lots of interesting things may happen. When you apply Hooke's law and you say the force is proportional to the displacement, there is a very critical assumption there. So what is the assumption that the force, the spring force is proportional to the displacement? What is the major assumption there? When is this valid? What type of displacements you need to have for Hooke's law to be applicable? It's the same thing like stress proportional to strain. What is the assumption there? Say it. Small, very small. And when I mean small, smaller than what you think. All right? When I mean small, smaller than what you think. So nothing that we will do can give very exciting sort of results because the displacements are very small. All right? So when you allow the displacements to be very large, Hooke's law is not applicable, and lots of interesting things may happen. But right now, the displacements are very small. So if you do a problem and the displacements are big, you know that your calculations are wrong. All right, so let me, I'm going to put all the forces down, okay? So we have the weight, we have the spring force, and you notice there is a minus there. That's one thing. And the second thing is the displacement is capital L plus U, because L is the displacement at the equilibrium location, and U is past that. And we really care about the values of U. That's what we will compute. And there is a minus sign there. So if you elongate the spring past, let's say, below its equilibrium location, the spring is going to try to bring the mass upwards. That's why we put the minus sign there. And the damping force, similarly, we take to be proportional to the velocity u prime. And again, if the displacement increases, right? So if u prime is positive and the mass is moving downwards, the damping force is going to try to move the mass upwards, so there is a minus sign there. And also, we're going to assume some external force, f of t. Now, when I'm going to write a differential equation for this problem, effectively, I'm going to write that the sum of the forces equal to 0, and there are two forces that are going to be canceled out. Can you see from this 4 equations which forces are going to be canceled out? How about the mass and k times capital L? Right? They will cancel out, right? Because the way we define capital L is the equilibrium location where k times capital L is m times g. So our equation is going to look, and let me just go rapidly to find it. Come on. Where's my equation? Here's my equation. The equation of interest is m u double prime plus gamma u prime plus k u equal f. Again, m is the mass, gamma is the damping coefficient, k is the spring constant, f is the external force. And this is what we need to discuss today. We need to discuss the particulars of the solutions to this equation. And the only thing that here is different from before is that all the coefficients that you see, m, gamma, and k, in this equation are positive. And you know what that means? For example, if you look at the roots of this polynomial, can you immediately see that the real part, or if the solutions are real, the whole solution, can you see that they are negative? I mean, gamma in this case is positive. So can you see that the solutions that you will get, we have negative real parts? Right? And the consequences of that will be that somehow the solutions will decay to 0. And so we will discuss this as we move along. Okay. So we are going to need some initial conditions. It's a second order ODE, so we're going to need some displacement. We're going to provide some velocity, V0, and that's what we want to solve. We don't need this. So here is just to keep things going, one example that there is no forcing term on it, okay? So the mass is 1/8, gamma is equal to 2, and K is equal to 24. So you put some initial displacement, U of 0 equal to 1/2, 0 initial velocity, and this is how the solution looks like. Okay, so you form the characteristic polynomial, and you can, you compute the real part and the imaginary parts, and you get basically an exponential decay plus an oscillation as the solution decays. All right, an oscillation defined with this frequency 8 square root of 2. Again, can you remind me, how do we get all these numbers? Where all these numbers came from here? Just remind me, because I forgot. How did you do the homework? How did you get all these numbers? What is the first thing to solve any equation of second order? What do you do? Characteristic polynomial, right? So s squared over 8 plus 2 times s plus 24 equal to 0. You compute the solutions, and what type of solutions you will get for this problem based on what you look here. It will be complex solutions, right, with negative real part, and the complex part is going to be this 8 square root of 2. Okay. So this is how the solution will look in this problem, and you can see that exponentially decays to 0, all right? And this is not a real oscillation, so we call it quasi-oscillation, but you can see really that the solution doesn't monotonically converges to 0. If it was monotonically, we were not going to have these cosines, but it goes down to 0, but at the same time, it oscillates towards 0, okay? All right. Now, if you don't have any damping, all right, so the equation will be a harmonic oscillator. So if gamma is not there, and I'm assuming for now that I have free vibrations, so there is no external force, so it will look like that. So the solution immediately will be an oscillation. So it will be, actually, if you form the characteristic polynomial, you will get purely imaginary solutions, no real parts, so you have cosines and sines, and this is how the solution will look like, okay? And the notation that I wanted to introduce, because we're going to use it in the whole lecture today, is the natural frequency omega 0. Omega 0 square is k over m. So I want you to remember the definition of the natural frequency. Natural frequency means no damping, no external force, all right, k over m. Pure oscillation. Now, before I move and I start introducing damping, I wanted to take this pure oscillation and rewrite the equation in a more convenient form that you will see in your textbooks. So this is what we get up to now, right? So the solution looks sines and cosines, okay? Now, what we would like to do is we would like to write the solution in the form of some amplitude r times cosine of omega 0 t minus some angle shift, all right? This angle delta. So effectively, we want to combine these sines and cosines to one cosine that looks like that times some amplitude r. And the way you make these two expressions equivalent is if you take this equation here, u equal r times cosine of omega 0 t minus delta, and you expand it, you will get the expression that you see in this equation, right? There is a minus there, so you will get a plus there, okay? So r times cosine of delta cosine of omega 0 t plus sine of delta and sine of omega 0 t. And if you match the original expression with a and b with this expression, you can see a is r cosine of delta, beta is r sine of delta. So r is the square root of a and of a squared and b squared. So if you have to do this, you don't need to prove it. Just directly write down the answer in your exam or in the homework. So r is the square root of a squared plus b squared. And if you divide these two equations, sine over cosine will give you a tangent of delta equal to b over a. Okay? So you can actually directly write the equation like this. Okay? And this is a much more convenient way to think of, so when we say this thing oscillates, sometimes you may get confused because you have a cosine and a sine, but you can actually combine them and you can see that you do get a pure oscillation here. Okay, and that's the period for this harmonic oscillator, 2 pi over omega 0. Okay, so we're going to use that as well in the analysis. So, I mean, I have an example similar to what I had before. So you, again, there is no damping. It's a pure oscillation, some initial displacement, some initial velocity. So the standard way, you get something like that. But you can combine those things. And I hope I have combined them somewhere. Here is R. Here is the phase shift delta. And here is a much nicer way to write the solution in terms only of one cosine. Mathematically, they're the same thing, but here it's easier when you see one sine only or one cosine, you can see why this is a pure oscillation. All right, and again, schematically, this thing oscillates to infinity without any loss of energy because there's no dissipation. Obviously not a very real case, but significant case because it is used as a reference case for lots of the things we will discuss later today. So again, R, remember the notation, R is this coefficient here is the amplitude, right? And this T, capital T, is the period for these natural vibrations. T is 2 pi over the natural frequency omega 0. Okay, damping now. So things will get very messy. I'm going to try to do some of the algebra and then only show you some schematics. And you can go and study the rest of the slides so we don't have to waste time with little calculations. So obviously, first we're going to do free vibrations, so there is no force on the right-hand side. So you go and you compute the solutions of the characteristic polynomial. And I mentioned before that when you look at, regardless if the solutions are real or complex, the real part, for sure, it's always negative because gamma is positive. So in that case, at least here in vibrations, we know that the real part is always negative. You're not going to have a growth of this to infinity. It's always negative. I see here we put a minus sign inside, okay? But remember, even if this gamma squared minus 4mk is negative, and you look only at the real part, right? It's negative. So here are all possible solutions you can get for this damped free vibrations. If y squared minus 4mk is positive, you're going to get basically two real solutions, and both of the solutions are going to be negative. So what happens to these solutions as t goes to infinity? They go to 0, right? And there's no oscillation. So don't think because you have a mechanical vibration problem that you always have oscillations. There is zero oscillation here. So in this particular case, right, this exponentially, they go down to 0 with no oscillation. Now we have the case of the square root of gamma squared minus 4mk being equal to 0. And based on that, by the way, we call this gamma squared, this value of square root of 4mk as the critical damping, because separates basically the type of solutions we get. And in that case, we get a solution that looks like that. And can you remind me why the solution looks like that? I forgot. Say it again. Double root. And for double root, one of the solutions will be e to the minus gamma t over 2m. And the other one will be what? T times that. You remember? Yes? All right. So t times that. So, and again, so this is critical damping, but that exponential term there dominates even the linear term in t. So this thing also dies to 0. And then, of course, we have the case of gamma squared minus 4mk being negative. And in that case, we get this exponential decay from the real part. And then we get cosine and sine. And I have defined here mu to be, the 4mk minus gamma squared divided by 2m, okay? So you can think of m being the quasi-frequency, if you like, of this damped system, okay? And pay attention because, since this gamma squared minus 4mk is negative, we wrote this as I times the square root of 4mk minus gamma squared. That's why the mu is defined like that, okay? All right. So the idea here is that in all cases, the solution goes to 0 as t goes to infinity, and you can actually think if there is damping, right? So there is no energy given to the system to sustain it, so everything will die out, okay? The only way to get something at long time will be to have an external forcing term that provides energy, but right now we do free vibrations, so that's not the case. So we're going to consider only the last case because that's the most interesting case to start with, okay? And so what I'm going to do is I'm going to take the A cosine plus B sine, and I'm going to write it the same way we did for natural vibrations as r times cosine of mu t minus delta. You remember how we did this before, right? We combine, so r is going to be the square root of what? R is going to be the square root of a squared plus b squared, all right? And the tangent of delta is going to be b over a. Look now, interestingly, if you take the absolute value of u of t, because the cosine in absolute values is less or equal to 1, you can see that the magnitude of u of t is bounded by r e to the minus gamma t over 2m. So the amplitude of u of t decays to 0, all right? So effectively, if I plot things, this is how it's going to look like. So this is the damped free vibration. There is no external forces. This is that blue curve. And then you can see that it's bounded by this r e to the minus gamma t over 2m. So there is a decay in the amplitude. And also you can see some of the relevance of parameters such as this phase shift delta. So for example, you can see that the time t equal to 0, all right? So this is mu t. So when mu t equal to 0, this is 1 there. So the amplitude is r times cosine of delta. Can everybody see that, right? So that's what you get, r times cosine of delta. And then you get the maximum here at what type of what angle? You get the maximum when the cosine becomes 1, and the cosine becomes 1 when the angle becomes equal to 0. So mu t equal to delta. All right, and that's why you see this phase shift delta there, okay, where you get the maximum in U. So again, this mu there serves as a frequency, all right? We call it the damped frequency for the system, but it's really, I mean, it's not like you are having a cosine or a sine that is sustained forever, because you can see that the solution dies to 0. So, you know, I don't mind if you call it a frequency or quasi-frequency, assuming that we understand exactly what is going on. All right, so let me, I told you I'm not going to do lots of the algebra, but I'm going to show you at least some of the formulas. So if you, I mean, someone would like to know what is the effect of damping, and the best way to do this is to compare the frequencies and the period of oscillations for the damped and the undamped system. So this is what this slide does. So it takes the frequency of oscillation for the damped system, which is mu, divided by the natural frequency omega 0, which is square root of k over m. And it plugs in mu. You remember mu, that's square root divided by 2m. And then you get this wonderful formula. OK? And this wonderful formula, in case you are interested, you can actually approximate it for small gamma to this nice formula, where you get rid of the square root. OK? Actually, I don't even, okay, so from, this is from the textbook, you know, he shows the derivation of this. But you remember, if you, from calculus maybe, if you have the square root of 1 plus x and x is small, do you know what is a good approximation of the square root of 1 plus x? If x is small? Square root of 1 plus x. What is a good approximation to get rid of the square root when x is small? This is very, very important. Actually, we're going to see this when we discuss power series expansions and the like in follow-up lectures. So what's a good approximation for the square root of 1 plus x? Or 1 minus x when x is small? You don't have to derive it here. You know, I'm curious. Anybody? This is used everywhere, actually. You will use this in your fluids courses, in your mechanics courses. Everywhere this approximation comes, in every course. Square root of 1 plus x is 1 plus x over 2. Thank you. All right? So, and similarly, square root of 1 minus x is 1 minus x over 2, and this is what you get here, okay? And so for small damping, mu over omega 0 looks like that. So what happens to the frequency when you have damping versus the natural frequency? What's the result? What happens to the frequency versus the natural frequency when you have damping? Gets bigger or smaller? Smaller, okay? So the frequency is reduced, and obviously for the period, the opposite will happen, and here is an approximation for the period. All right, so these are for the comparison, so we don't want to say very much. Now, notice that, can you remind me this gamma equal to 2 square root of km? Have we seen that value of gamma before? Gamma equal to 2 square root, maybe you don't remember this, maybe gamma square equal 4 times km. Where is that thing coming from? Gamma square equal 4 times km. Where have we seen that? Gamma square equal 4 times km. The critical damping, all right? So you can actually see here that the natural frequency of mu goes to 0 when gamma gets close to the critical damping, and the period gets equal to infinity. You expect that, right? I mean, critical damping is when we go from no vibration, from no oscillation to oscillation, so you expect that you will get exactly this correct result. So this is related with what we're discussing before with the separation, the three different type of solutions and the critical damping. I'm going to come back to this, right? So this is a good plot of the three solutions. So when gamma squared minus 4mk greater than 0, we have the situation of overdamping, okay? So there is no, that's the curve that you see there. There is no oscillation, right? E to the R1t and e to the R2t, both of them go to 0 because R1 and R2 are negative. Then we have the case of the critical damping, which is case 2, and it can correspond to either this red curve or this black curve. And then we have this exponential decay with oscillations, which corresponds to this blue curve, okay? This is the underdamped case. So we have overdamped, critically damped, and underdamped. There is an example in the notes that maybe you already have studied, and I don't really want to say any details. I just wanted to show you the effect of damping on a very simple problem without any forcing terms. So you can actually see the solution. The dotted solution corresponds to 0 damping, all right? And you can see the solution with very small damping, and the initial conditions are the same for both systems. So you can see a little bit of damping forces the solution to actually decay to 0, the changes in the frequencies are very small, right? It's hard to actually see the differences because the damping in this case is very small. But even a very small damping has the effect of actually killing these oscillations and exponentially giving you a 0 solution. All right. I need to be sure that I go fast enough to tell you a little bit about forced vibrations, otherwise we will be in trouble. Okay, there it is, forced vibrations. That's what I wanted. All right, so, so we're going to now put an external force, and we're going to take an oscillating external force, so we can discuss resonance. So we're going to take a force that is of the form F0 cosine omega t. So remember, when now you see omega, omega is going to be the frequency of the external force. Remember the damped frequency, we call it mu, okay? Omega here is going to be the frequency of the external force. All right, so let me just write down the general solution. The general solution will be the solution of the homogeneous system. You already know how to get those. We already discussed them actually in the last 10 minutes. And then you're going to get a particular solution corresponding to this external force. And we already have seen in the previous lecture, the particular solution, we have a combination of a cosine and a sine omega t. So that's the homogeneous, and that's the particular solution. Now, let me be, so I can save time. Can you tell me what long term, do I really care about this solution? About the homogeneous solution? Do we care long term, like at time to going to infinity, do we care about the homogeneous solution? Why not? Because it goes to 0, so we don't really care. So effectively, you can see this capital of U of t as being the steady-state solution, right? So in engineering books, for example, they're not even going to bother to give you the homogeneous solution because at long-term time, the homogeneous solution has died out. However, the homogeneous solution is essential because it gives you the effect of the initial conditions, right? It takes care of the initial conditions. And so the only time where you will need to actually maintain the homogeneous part is if something fancy happens with the initial conditions. If not, basically, capital of U of t will be the steady-state solution. All right. So we can bypass all of the slides because the homogeneous solution goes to 0, and we're only interested for the transient solution. So there is an example to convince you actually that that's the case. If I can, so for this example, I'm only going to give you how the solution is going to look like, right? You can solve the homogeneous problem and then add A cosine of t and B sine of t. A particular solution comes to be like that. You should be able to compute this, okay? And actually, I think there is a picture. I want to show you a picture. This is a nice picture, all right? So look at this picture that gives you the full solution to the problem, including the null solution and the particular solution. And then it gives you the steady-state solution, all right? And the difference of the two is this transient solution, right, from the homogeneous problem. And you can see after, let's say, time 5, it's 0, right? So if you're looking literally for long term, it is only the particular solution that defines the response of the system. Okay, so we don't really care too much about the null solution, but the null solution, of course, is essential to take care of the initial conditions. And in this example, I derived the initial conditions, but you can see here the effect of the initial condition is not felt after some time. I mean, if I do something now, the system forgets basically after a few minutes, it will not remember what the initial conditions were, and it is the driving force, 3 cosine of t, that defines what's going on. Okay. And of course, if this is the steady-state solution, we can write it as an amplitude r with a frequency omega. That's the forcing frequency, and then some phase shift delta. And these are the formulas for r and delta, and are derived basically by plugging in the particular solution in the differential equation, and immediately you will see what the coefficients A and B are and what R and delta is. There's nothing really to prove here, right? So you take this, you plug it in the differential equation, you use the definition of omega 0 squared being k over m, and that's R, and that's sine and cosine of delta. So the rest of this lecture, actually, and the slides, is to qualitatively tell you what these equations mean. And they really mean a lot of things that I would like you to study them, because I see I only have 7 minutes to tell you something about them. But the best way to study them is to plot them for different values of omega 0 and different values of gamma and see what is going on. So let me do the following thing. I'm going to find a slide, just to save us time, that introduces the picture. Anybody has the slides open? Where is the picture? What are we? 130. 135. Let me try 135. Thank you. All right. So if you plot the amplitude, okay, so this amplitude is Rk over F0, right? F0, I will assume, is the amplitude of the external force, and I am plotting it versus omega over omega 0, all right? And I am having sort of a dimensionless definition of the damping. I'm defining this capital gamma to be gamma squared over mk, because that coefficient comes to be very essential when you look at the previous equations in defining the behavior of the system. So, so omega equal to omega 0 is, how do we call that situation when the external frequency is the same as the natural frequency of the system? What's the name for that? Critical order, that's the resonance, all right? So basically, the external frequency is in harmony with the natural frequency of the system. And as you know, in that case, the amplitude of the oscillations goes to infinity, but only for the case of very small damping, all right? So you can see when you are at omega equal to omega 0, all right? I have to zoom directly and see in the picture for literally when omega equal to omega 0 and gamma equal to 0, that's when R goes to infinity. But I have the same effect, sort of, but for omega that is slightly smaller than omega 0 if there is some small damping. Can you see this? That the amplitude that you get has its maximum near omega 0, but not at omega 0, for a smaller value. Can you see that? Omega equal to omega 0 is if you take the vertical line at 1, which is this dotted line. But for smaller gammas, the maximum of R happens for omega a little bit less than omega 0. OK? So that's, you need to remember that the resonance is less significant if there is damping, OK? And this is a nice way to see it. And if there is, in this particular case, if you increase the damping, what do you observe? Do I have a maximum of, in the amplitude, does the amplitude of the oscillations has a maximum as the damping increases? Look, for example, here in the case for gamma equal to 2. What do you observe? Does R have a maximum? Yes, it does have a maximum. What is that maximum? F0 over K, which is the static displacement, basically. OK? So in that case, I don't really have resonance. All right? So the maximum value is at omega equal to 0. OK? And the amplitude decays from that value down to 0. So again, what you know about resonance for omega equal to omega 0, it is true when the damping is very small, all right? So in particular, in this case, when the damping is equal to 0, when the damping is very small, still resonance happens, but at a frequency that is less than omega 0. And for damping a little bit larger, you actually don't get this resonance effect. You don't have a maximum R happening at some frequency omega. The maximum R happens at omega equal to 0, and the amplitude R decays after that from that maximum value. All right. So there is in the slides actually, there is proofs of why these plots look like that. But I think if you keep in front of you the plot and you understand what it means, you have everything you need. So let me just say the following regarding the phase shift angle. If the external frequency is 0, the response is in phase with excitation. Okay? So basically, in that case, delta equal to 0. If you're very close to the natural frequency, omega equal to omega 0, you can see from these formulas that you are behind from the excitation in the response by an angle pi over 2. And if omega is very large, you're behind from the excitation by an angle of pi. OK? So you need to remember these three extreme cases when it comes to this phase lag. And there is an example that plays actually for different values of the external frequency omega that discusses these three different extreme cases. So you know what I want to do is 1119. Can somebody tell me the slide for the, what is it, the, come on. $141. So let me very rapidly go, and I'm going to try to do this in 1 minute. Okay, that's always a challenge in my life. So we're going to have an external force F0 cosine omega t. There is no gamma. So we had, this is a pure oscillation if you look at the homogeneous problem. So it has sines and cosines with the natural frequency. And then you have a particular solution that looks like this. Okay? So if you put some initial conditions of 0, all right, you can combine things from the homogeneous solution and the particular solution, and you get something that looks like this. Okay? So again, this is the solution for not damping, all right, with an external frequency in the force omega, and omega 0 being the natural frequency. And actually, you can see in this example right away the resonance effect. If omega equal to omega 0, this goes to infinity. But if I take this and I rewrite it, and this is very important, I can, you know what? Can you rewrite, if you have difference of cosines, can you do some miracles and write it nicely as such? You remember we had, come on, where was it? We had cosine omega t minus cosine of omega 0 t. Can I write it as that? Sine of omega 0 minus omega t times sine of omega 0 plus omega t over 2 times 2. You remember from trigonometry? All right? So what do I care about this? I care because now when you look at this expression, you can see there is a fast oscillation that is defined by the frequency omega 0 plus omega over 2. And then there is a smaller oscillation, slower oscillation of the amplitude defined by the frequency omega 0 minus omega over 2. And if you actually plot this, this is how the solution looks like. So the amplitude, which is this bracket, is this dotted line that you see. All right? It moves slowly in this particular example with frequency 0.1. And the actual solution, all right, it moves with frequency much rapidly with frequency omega 0 plus omega over 2. And this is what people in acoustics call beats, okay? And it has lots of applications in many areas of engineering, okay? So again, these are how the solutions look with no damping, amplitude varying with this slow frequency, and the solution varying with a much rapidly frequency omega 0 plus omega over 2. All right, so I think I'm done, okay? So, for those who are interested on applications of these things in circuits, the equations and everything looks the same. You just need to reinterpret the results of mass, damping coefficient, and spring constant to corresponding things from circuits. So with that said, I will see you on Friday with a new topic.